Okay, the stuff that, I'm trying to make these assignments really short. The stuff from the 7-2 assignment, you already know. There's nothing new in here at all. It's taking the stuff that you did in chapter 6, section 1, and using fractions as integers. That's it. There's nothing new here at all. So what do we do with a problem like this? What's our property of exponents tell us here? Well, what if I'm multiplying 3 to the 5/3 times 3 to the 1/3? What's the property of exponents that applies? Okay, I'm multiplying like what? Bases. Yeah, what's my like base? 3. Okay, so if I multiply like bases, what does the property of exponents tell me I need to do? If you multiply like bases, you add the exponents. Very good. Okay, so shouldn't this just then be 3 to the 5/3 plus 1/3? Right? So what is 5/3 plus 1/3? 6/3. Which is 2, okay. So my answer is 9. Yeah. Good. Okay, what's the difference between that and that same problem if we had an x in there instead of the 3? Nothing, except that last step would have just been x squared. We couldn't have turned it into a number, right? Okay, another one. Let's just practice these a little bit. How about something like this? Okay, take a second, look at that. Nobody say anything yet.
We didn't mean
Put
that.
that away. All phones away. Phones away. Put it away. Don't want to see them. That's a 1/2. Yeah. Good. Okay. Good. The property of exponents here. If I'm taking a power to a power, I multiply the exponent. So I'll just multiply that 1/2 by the 2/3. Good. So I end up with 5 to the 2/3 times 1/2, which is what?
2 to the 6th.
That's my answer. 5 to the 1/3. Okay, we'll get some practice. Multiplying fractions is easy. Multiply straight across, top and bottom.
Alright. I'm not very smart.
Okay, let's try another one.
No, you're not.
Okay. Okay, what about one like this? What if we have, let me make this a little hard. What if we have 3 to the 1/4 times 7 to the 1/4? Now, do I have like bases there? No, I don't, right? I don't have like bases, so I can't just add the exponents. Is there anything that is alike there?
The integers.
The exponents. Aha, look at that. The exponents are the same. So can anybody see something here that we can do with this?
Multiply.
Good. Yeah. Good. I could undistribute that 1/4, couldn't I? I could write that as 3 times 7 to the 1/4, couldn't I?
Yes.
Right? And what's 3 times 7?
21.
So that's 21 to the 1/4. Right? Okay, now I want to point something out though. What if I had something like this? What if this looks slightly different? What if that was 3 to the 1/4 times 7 to the 1/3?
Oh,
Is there anything that's alike there?
no.
Can I do anything to that?
No.
Can't. Nothing I can do.
So that's the
That's
answer?
the answer. You can't simplify that any further.
Put it in there. That's the,
Well, you could make it. What do you mean by solve it? Well, I could find an approximate answer. I mean, but no, that is the answer. That is the answer. If I put that in a calculator, I'm going to get back a decimal that's an approximation of the answer. So I could, if I wanted to, I could make this approximately equal to some decimal. But that's only if the question specifically says round a decimal, right? Otherwise, that is the final answer. That's the exact answer. Okay? You can't make it any simpler. All these other ones we could make a little bit simpler, right? But that one you can't. Okay? All right, another one. How about, okay, something like this. Whoops. Say it again.
Is it hard to like divide all these? Or is it like-
No, it's not hard. So what if we have 7 to the,
He's been saying that since chapter 1.
what about that one?
That'd be 1.
Okay, what's the property that applies here?
The bases are the same.
Bases are the same. If I divide like bases, I
Add.
subtract exponents. Okay, so
3 minus 1.
yeah, so that's 7 to the 3/5 minus 1/5, which is what?
2 over 0.
7 to the 2/5.
Oh.
Good. Okay, now I want to show you one that's kind of awkward a little bit. This one, what if we flip those exponents around?
Yeah, have a negative over.
Ah, okay. Well, okay, good. So now, remember how this works. We said that we're gonna work, if we divide like bases, we were a little more specific in the book about this. We said you always subtract the exponents, but you always keep the base where it has the most power, and subtract the other exponent, right? Exactly, so we can put a 1 on top, and it's then on the bottom, it's 7 to the 3/5 minus 1/5, so it's 1 over 7 to the 2/5, which honestly, I think is a fine answer, but mathematicians don't like to have numbers, like remember how we didn't like to leave square roots on the bottom in chapter 5? Okay, well, this is a root, isn't it? This is really a 5th root of 7 squared, right? So it's the fifth root part. Because I have a fractional exponent, we don't like to leave that on the bottom. So what I want to do instead is I want to write this in a way so that I have an exponent on the top but not the bottom.
Multiply by 7, negative 7.
So what could I do here? You see a way I could do this?
Multiply.
Okay, well, I could write it as 7 to the minus 2/5, but the negative exponent still means it's on the bottom. We want to write our answer in terms of positive exponents. So I'm going to have to multiply the top and the bottom by something. Okay, what do I need to multiply the bottom by? What power of 7 do I have to multiply the bottom by? So I just get a plain old 7 in the bottom, an integer, instead of, in other words, 7 to the 1. How could I multiply the bottom so I get 7 to the 1 instead of 7 to the 2/5? If I multiply top and bottom by 7 to what power? Now, if I multiply the bottom by 7 to a power, think about how we're going to deal with the exponents.
Negative.
Say it again.
5 over 2.
Well, okay, now if it's 5 over 2, when I multiply like bases, I add the exponents. So is 2/5 plus 5/2 equal to 1? No. 2/5 plus what equals 1? 3/5. Right? So I'm going to multiply the top and the bottom by 7 to the 3/5, and if I do that, then on the bottom, I get 7 to the 2/5 plus 3/5, which is 7 to the 1, right? What do I get on the top? 7 to the 3/5, right? So that's the way technically we want to write that one, so that the fractional exponent is positive in the numerator and not the denominator. Okay. Now, say it again. Yeah, I only give you one problem like this, but yeah, you do. You do. But remember the trick. The trick is just, let's do one more of those, just so we make sure we have the hang of it. Okay, what if we have one like this? What if we have 5 to the 6/7 over 5 to the 2/7. Okay, there's another way we could do this, by the way. If I wanted to, I could just multiply both the top and the bottom. I don't even have to simplify this first. If I just want to get 5 to the 1 on the bottom, I could even skip a step, right? Couldn't I just multiply both the top and the bottom by 5 to some power? Right, we're going to have to fill that in. To get 5 to the 1.
5
Yeah, what, does that make sense? 2 sevens plus what is gonna be 1? Well, 7 sevens, 5 sevens, right? So I'm just gonna multiply both the top and the bottom by 5 to the 5 sevenths. And on the bottom, I'm gonna get, yeah. Right, let me just write it out so we can just see. On the bottom, we're gonna get 5 to the 2 sevenths plus 5 sevenths, which is equal to, on the bottom, just 5 to the 1. What do we get on the top?
That's
It's the same thing, but with
5 to the.
So what's 5 to the 6 sevenths times 5 to the 5 sevenths is 5 to the,
6, 7, 8, 9.
what's
11
5?
sevenths.
11 sevenths.
I have 6, 7, 8, 9. I didn't get on my fingers. Add that to mine. I was Einstein, so I just tried it.
So that's it. Either way, you can do it either the way we did the first one, that's fine, or the way we did the second one. It's really the same number of steps. We just want to get an integer on the bottom, okay? Anything else? Let's see.
Is this all 7.2?
Yeah, it's just 7.2.
That's easy.
Yeah, it's like I say, 7.2. There's really nothing that new. There's one new thing. I'm going to show you a great trick. But this is new. Okay, how about this? What about that one? Anything alike?
The thingamajigers.
Exponents. And when exponents are alike, what's our trick? This is your expertise here. What do we do if we have like? Good. Okay. If we have like exponents, if we have like exponents, we can factor them out, right? Pull them out of both top and bottom.
Oh yeah.
So we could write this as 70 over 14 all to the 1/3. And 70 over 14 is just 5, right? 70 divided by 14 is just 5. So there's our answer. Okay? All right. Okay, how about one more of these, and then I think we're good to move on. Okay?
The fighting's hard.
Okay, what are our options here?
Distribute out the 6 first.
Okay, good. We could distribute the 6 first, or we could do what?
Do the like bases in the parentheses.
Okay, or we could multiply the like bases and add the fractions. In this case, I would recommend, it's probably easier to distribute the 6. How come? Not that it makes that much difference.
So we don't have to do that.
But when I distribute the 6, what happens in one of those two cases? If I distribute that 6.
They'll turn into 1.
One of those is nice.
Second one.
Second one, yeah, 6 over 3, that reduces to 2. The fraction goes away, so why not? So then we get 2 to the 6/4, which is gonna reduce to what?
3 over 2.
3 over 2 times 2 to the 6 over 3 is 2 squared. So if I have 2 to the 3/2 times 2 to the 2, like bases, what do we do to the exponents?
2 to the 3 over 2. Add.
Add them. So I get 2 to the 3/2 plus 2 over 1. Okay, now, we gotta remember, how do we, and you guys know this, we just don't do it very often anymore. But how do you add fractions? What if I have 3/2 plus 2 over 1? Common denominator, very good. So I gotta get a common denominator, in this case of 2. So I'll just multiply by 2 over 2, and that's gonna give me, 3 over 2 plus 4 over 2 equals what?
7 over 2. 7.
7. So my answer is 2 to the 7/2. Okay. All right, so that's enough of that stuff. I think you got it. That's really, and there are some problems I could assign harder problems, but I think it's overkill. I mean, if you know how to do that, that's sufficient.
Let's do 7.3.
off on. We're not there yet. I'm gonna take this one at a time. Now, next thing, simplifying radicals. You know how to do this also. What if I asked you to simplify the square root of 50? Remember, think back to chapter 5. Yeah, nobody likes this stuff very much, but it's, you gotta know it. Well, the short answer is, this is likely to be on that compass test.
Really?
Yeah.
Oh,
Say it again. Good. Okay, what we're looking for here, and I will put a sheet on Moodle that has a list of the perfect squares, perfect cubes, perfect fourths, etc. Just so you have something to look at. Those are good to know, though. So if we look at our list of perfect squares, 2 squared is 4. What's the next one?
16.
No. 3 squared is?
9. 16. 25.
Well, 25, jackpot, right? That fits.
36.
50. Okay, so I could rewrite this as the square root of 25. And always put when you're doing these, remember, always put the one that works out nicely. Put the perfect square or the perfect cube if you're doing cube roots, etc. Put that one first, because that's going to end up being outside. So we get 25 times what is 50?
2.
2. So we split it into 2 separate radicals. 5 squared 2, we're done, right? Now the same principle works if we're doing higher level roots, which we do in chapter 7. So what if we had something like, let's say, the 5th root of 1215. Okay, these numbers get big in a hurry, because when you start talking about fifths and fourths and things like that, I mean, those grow fast. So let's make a list of perfect fifths here. Not one, we don't need one. 2 to the 5th is 32, and after that they start to get big in a hurry. 3 to the 5th is going to be 243. And 4 to the 5th, now they start to get really big.
1,024, isn't it? I'm just guessing.
I'll take your word for it.
Baller.
Okay.
I heard him.
5 to the 5th is going to be really big. 5 to the 5th is, what is it?
3,100 and something. I'm not sure.
3,125. Okay, so obviously now if we look at our list of fifths, that's too big, right? So the only ones we need to really look at are these guys. The question is, I guess, now that's not going to go into it, is it? No. But that one could. That one could, right? Okay, so 243. Let's see, 243 does go into that, right? 5 times, it works out perfectly. 5 times 200 is 1,000, and 5 times 40 is 200, and 5 times 3 is 15, right? See how we got that? That's kind of did everybody see that? If we say 5 times, whoops, I think off a little bit. 5 times 200 gives us our 1,000, right?
Oh, yeah.
5 times 40 gives us our 200, and 5 times
315.
3 gives us our 15, right? Okay, so then that does work, right? We can break this up. We can break this guy up into the 5th root of 243, which is what?
3.
Right? That's just the 5th root of 3 to the 5th. So that's going to be an integer times the 5th root of whatever we need to get 1215. Well, we said that was just 5. Okay? Because 5 times 243 equals 1215, right? So then this just becomes 3 times 5th root of 5. Okay? I don't think that's a really that important thing. I'm going to give you a couple problems to do, but not very much. Maybe 1 or 2. Just so you get the hang of it, so you've done it a couple times. But it's not that big a deal. Okay, so what about variables? Variables makes it easier, not harder. When you're dealing with variables, the bases are really easy to see if they're when they have like bases. You don't ever have to even turn anything into a number. You just leave it, you just simplify the exponents, and that's that. I'll give you a quick example. we have something like x to the 1/3 times x to the 1/5, it's obvious, we have a like base there. What is it?
X.
X. So my answer is just x to the 1/3 plus 1/5, because I'm going to multiply like bases, I add the exponents. See if you can do this in your head. What are those going to add up to? Just take a second. Nobody say it out loud. Try getting common denominator. This is good practice. This makes you good at algebra, good at mental math.
Oh, I don't know that.
Everybody got it? 815, exactly, right? Because now think what we're going to do. We're going to have to multiply the first one by 5/5, right?
Got it.
And the second one by 3/3. So we're going to get 5 on the top in the first case, we're going to get 3 on the top in the second case, and 15 on the bottom, right? So we get x to the 8/15. No big deal, right? Okay, so, and I'll just leave it at that. We don't even really need to do anything extra with the exponent, or with the variables, because the variables actually make everything we just talked about simpler. Okay, here's the thing I wanted to show you, the last part. Last part.
This is hard.
It's not, but you gotta pay close attention. If you pay close, these people, this is something, if people looked in the textbook and tried to get this out of the textbook, this would be hard. But this is a fantastic trick. If you get this now, this will save you lots and lots of frustration. Because it's not, I will make this easy for you, I promise. Okay, so what if we have something like this, let's say. 4th root of 10 x to the 5th, y to the 8th, z to the 10th. Okay, and we want to simplify it. I'm going to show you a great trick for doing this in one step. Okay, here's what you do. Here's what you do. Now, the first time I show this to you, I'm going to write a couple things down that you'll never have to write down again. What does it mean? What's the fractional exponent equivalent of a 1/4 power? Taking something to the 1/4, I think I just said, taking a 4th root of something is the same as taking it to what power? The 1/4, right? Sorry, I just gave it to you. Okay, so this is the very same thing as writing 10, the quantity 10 x to the 5th, y to the 8th, z to the 10th, to the 1/4, right? Okay. The hardest part, by far, of a problem like this is the number part. The variables are so simple. So we'd have to ask ourselves, can we simplify the 4th root of 10? Well, no, we can't, because the 2 to the 4th is 16. So there's no perfect 4th that's ever going to divide into 10. So we're stuck with that. In other words, the 10 is going to be stuck inside the radical. There's nothing, I can't take any of it out of the radical, right? So that part's there. Now, what about the variables? Okay, the variables are really simple. What would I do? What does my property of exponents tell me I do if I take powers to powers? In other words, what do I do with that 1/4 there? Okay, yeah, I'm going to distribute it through, aren't I? And multiply it by each of the exponents. Agreed? So I'm going to get, so the x is going to become x to what power? If I multiply 5 by 1/4, what do I get? 5/4, right? 5/4, okay. What about the y? The y is going to become y squared, right? Because 8 divided by 4 is just plain old 2, it's an integer. And then the z, okay, becomes 10 over, well, I'm going to leave it as 10 over 4. Okay, but we could reduce it further. But I'm going to leave it, I want to leave it in terms of whatever that original index was. Okay, so I'm going to write it as 10/4. Okay? Now, what does that mean? What does it mean to be x to the 5/4? If I write these as mixed numbers, and someone already said it, I think Andrew said it, what is 5/4 as a mixed number? 1 and 1/4. Okay, so I could write this as x to the 1 and 1/4, right? If I write that as a mixed number. The y is, there's no need for a mixed number, it's already just a plain old integer, right? So I get my y squared, and my z, should have made z a different color. 10/4 as a mixed number is what? 2.5, 2 and how much, let's leave it in fourths though. 2 and how'd you get that? Okay, 4 goes into 10 2 times evenly, right? With 2 left over, right? Okay, now watch what we can do with this. If I split this up then, that's the same thing as saying, this is the same thing as saying x to the 1 times x to the 1/4, isn't it? Right? 1 1/4 is just 1 plus 1/4, right? Everybody agree? This is the same thing as y squared. That's easy. This one is the same thing as saying z squared times z to the 2/4, right? Okay, now we're not gonna have to do all this stuff, but I want you to see what just happened. What happened was I was able to write at least parts of the powers of these variables as integers, and then I was stuck with some remainder left over, right? That was still a fraction. But when we get our final answer to this problem, this problem up here, it's going to look like two parts. It's going to look like an outside of the integer, the simplified part, times the 4th root of what got stuck inside. Okay, what part's going outside and what part's going inside? Well, let's look at each of these. The 10 is stuck. The 10 is stuck inside. What about the x's? Well, we ended up with, yeah, look what happened. We got x to the 5/4, so we got two parts of that. We got an x that made it out, an x to the 1, and then we got an x to the 1/4 that needs to be stuck inside. Well, there's my 4th right there, right? So that's the same thing as x to the 1 inside the radical, because there's the denominator. See what I'm saying? So what a trick. That's a great trick. If I just distribute the power, right, multiply the fraction through to all the exponents, write that number, think of that number as a mixed number, then the integer part goes out front, and whatever the remainder was, in this case it was a 1, that's what stays inside the radical.
So then 2 z's go out.
Exactly. And the y's all go out, don't they? There was no fractional part left over. So the y squared just goes out front. The z's are going to split. I'm going to get outside a z squared, and inside I've got, here's my remainder, right? Was it 2? So inside I'm going to get a z squared also. Okay, now let's try one without all the writing. Let's just try to write the answer down. Let's see if we can do this. So what if we have the 4th root of 11 x to the 7th, y to the 5th, z to the 16th. Okay, that's going to equal some outside stuff times some inside stuff. Okay, what about the 11? Stuck on the inside. I can't simplify that. The 4th root of 11, there is no perfect 4th that's going to divide evenly into 11. So that's all stuck inside. Now what about, let's make the x red. So what about the x to the 7th? What's going to be the denominator that I'm going to distribute through? It's 7 what's? 4ths, right? Because that's the denominator. That's the same as a 1/4 power. So 7/4 as a mixed number is what? 1 3/4.
So then 1x out.
Ah, okay, good. Perfect. So we get x to the 7/4, which means we're going to get x to the 1 and 3/4 done with the x's. See? What about the y's? Let's make the y's blue. Yeah, so we're going to get y to the 5/4 as a mixed number. That's 1 1/4. So y to the 1 and 1/4. Right? Okay, what about the z's?
Oh, well, 4 goes in there.
Yeah, I get z to the 16/4, which is just 4. So it's all outside. That's it.
Do we have to put the 1x?
No, you wouldn't, in fact. You wouldn't put that there. Okay, one more of those. Now that's it. That's it for today. Let's see if we can get, I'm gonna give you a little harder one. How about,
What is that? Is that a 10?
that's a 10.
Yeah.
Okay, the hardest part, the variables are easy. Variables we can do right away. The hardest part is the number. Is there a perfect cube that goes into 16? Think about the perfect cubes. 2 cubed is 8, 3 cubed is 27, that's too big. But 8 goes into 16, right? Twice. I could break that 16 up into the cube root of 8 times the cube root of 2, right? And so I'm gonna, what's the cube root of 8? 2, right? And then I've got a cube root of 2 that's stuck in there. That's the hardest part. The variables are simple. Okay, what about the x's? I've got an x to the 1/3. So where does that stay? Yeah, it's got x inside, right? Okay, I've got y to the 10th, so that becomes the fraction y to the 10 as a mixed number. That's 3 1/3.
Boom, got it.
I won't even write the 1, right? Z,
C's cubed outside.
yeah, I get z to the 9/3, which is done.
Smaller.
Okay, how about that?
I don't know how you did with the 5 and 8 and
You mean with
like how?
that and that? Okay, let's look at just that part. So if we have the cube root of 16, I'm going to split the 16. I'm going to make that the cube root of 8 times 2. Oops, cube root, right? Okay, and so that becomes the cube root of 8 times the cube root of 2, and the cube root of 8 is 2.
Oh, that's just.
Okay? That's how we got it. All right, very good. That assignment is actually not totally done, but it's very, very close. So I will have that one up. Oh, it's like 10 problems or less.
Baller.
Okay?